All right. Hey, everybody. Hope everyone is doing fine after all those storms last night. Uh, all right. So I also hope everyone had a decent time doing the homework. Uh, that will be the last homework we do with derivations, which I know is going to make a lot of you guys sad, but no more derivations, at least as part of homeworks. They'll be on the exam though, so don't worry. You'll still have some derivations to do. Uh, but also in the homework was uh, an introduction to circuits. So just getting to know logic gates and the input-output tables. Today we're going to cover more about circuits. So on Friday, we did a problem you guys are going to see on this homework where we turned a description of some function. So here it was a description of a pump circuit functioning, and we turned it into a circuit diagram that would, with the logic gates that we learned so far, perform this function that's needed by the pump operators. And so I took you through that process. The first part of it is determining which atomics are going to stand for what inputs and outputs. And then the second part of that is drawing up your table of operations. The third part of that is turning that table of operations into a TFL well-formed formula using something like disjunctive normal form. And then the last part is turning that well-formed formula into a circuit. So there's a bunch of translations that happen from the word problem to the circuit diagram. Okay. And then we also made a 1-bit adder, which was another like fairly simple circuit. We turned these possible algebraic operations on binary numbers into an input-output table. So today we're going to talk about efficiency with circuits. So the thing that computer engineers are concerned with, or just circuit designers in general, is not necessarily finding a functional circuit. It's finding an efficient functional circuit. So one that is going to use the least amount of resources, either time or heat's a consideration. So the more logic gates you have, the more heat being emitted by the circuit. So there's these constraints, that other constraints besides just designing the successful thing that's a concern. All right. Here's a really old computer. I think when I put this in the slide last year, I forget the name of it. It was like one of the first computers ever invented. Here you have like can be specified. Now we've got keyboards. All right. So one thing you guys might have noticed is that different gates can do the same computation. And this was a fact that so when you were figuring out how to, for example, it's supposed to be and, into a series of down arrows with the same functioning, you were figuring out that different TFL operators or different TFL form formulas can have the same truth function. And some of them have less connectives than others. So we can potentially find circuits that have the least amount of logic gates. So if we go back to this pump circuit, it's got 5 gates. But perhaps we can come up with a circuit that does the same thing, but with only 2 gates. And that same idea applies to disjunctive normal form. Normal form is going to give you the biggest, most ugliest TFL well-formed formula that matches that truth function, smallest one. Oh, I didn't want to go on. So the reason there are these different gates is because they're easier to use. Not all gates are made the same. So I think NAND gates can perform all the other gates' functions if you string them together. So there's these different considerations based off like non-logic functioning facts about the gates. But just in general, as far as efficiency goes, the more gates you have, the slower things tend to go and the more energy consumed. So here are two words you guys will have to be familiar with. There's depth and size, efficiency. So the depth of a circuit is the largest number of gates that a single continuous path should encounter. So if we go to our 1-bit adder here, we can follow that hits the most amount of gates. So if we follow this A wire, 3. Now let's see if we can find a wire that hits more than 3. We can't. So is 3. The size of the circuit is the total number of gates in it. So the size here is 1, 2, 3, 4, 5, 6. All right. So these are different measures of, and they're the two that engineers are like broadly concerned with. So the less gates you have, the better, and the less depth. Okay. So you guys might remember that. So we made a 1-bit adder on Friday. So it performed these operations: 0, 0, 0 plus 1 was 0, 1. Sorry, 1. And then 1 plus 1 was. So if you remember, representing the first digit just to make us, oh, it's right here. Yeah, it required us to do was performing the first digit output. So when A was 1, it would come out with a 0. Well, the functioning here is mimicked by a new type of gate, the either or gate, XOR gate. So since we have this gate now with this one gate, because it performs that same functioning, right? Or it outputs 1 when it's neither or, right? Thing we tried to build with the circuit for the pump machine is this entire circuit. Obviously, having this gate do it in one efficiency. And if you imagine a lot of like complex machinery, 100 of these same or thousands of these same circuits perform the same function. So 5,000 times more efficient. Okay, so here's an example of how we can have, with the addition of this gate, a new way to draw up the circuit. Now it's size 2, depth 1. So size is the number of gates, this amount of gates a wire has to travel through. All right. It's showing how we make a 2-bit adder out of a 1-bit adder. If we turn all of these boxes that are the equivalent of this circuit, so size 3 into 2, 1, it removes like 12 gates from the little efficiency tweaks in the more fundamental modular circuit. You can imagine a 4-bit adder would have even more adders strung together. The way the 2-bit adder functions is that it takes as input two 2-digit binary numbers and gives as output a 2-digit binary number with a carry digit. Looks like for a 2-digit adder, if you remember the 1-digit adder, so as you move into more try and add more bits together, it increases exponentially, the same way that that it was true for truth tables. Okay, and so here is an image of, so let's see how efficient, let's see, of this circuit. So try and figure out on your own the depth and size, and then we'll do this together. Okay. So were you guys having trouble figuring out the, oh. It says my speaker's not working. Can you guys hear me? Hey, Maddie, can you try talking just to see if I can hear you guys?
Can you hear us?
Yeah, okay. So did anyone have trouble figuring out the depth or size of the circuit? Okay, so to figure out the size, you simply count the number of gates. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 gates. And then the depth is the most amount of gates that a wire has to run through. And this one's a little bit more difficult. So I'm going to say it's probably starting from here and going through 1, 2, 3. No, that's not it. Maybe starting from here and going through 1, 2, 3, 4, 5, 6, 7, 8. Did anyone find a path that took them through more gates? Trying to think if this, no, I don't think so. One, two, three, four, five, six, seven. Yeah, I think 8's the most. Okay, so we found a path that, there's 2 paths that take us through the most amount of gates, here or there. So significantly, maybe inefficient circuit, because we found a way to replace each of these chips, these adder chips, with something more efficient. So here's the revised 2-bit adder, and now let's calculate the total efficiency. So for the size, it's 1, 2, 3, 4, 5, 6, 7. So more than twice as efficient as far as size is concerned. And then the depth, so the most amount of gates a wire has to pass through, has to go through. And I think that is 3. So this path right here, 1, 2, 3. All right. So that's efficiency. Just showed that drastically changed the efficiency of the circuit by trying to replicate parts of it using the functioning of other logic gates. So here, this version of the 2-bit adder is something that would be analogous to using disjunctive normal form to figure out the circuit. And disjunctive normal form is not necessarily the most efficient way to do this. All right. So here's something you can actually buy on Amazon if you guys wanted to. So a 4-bit adder chip. They don't come really in, adders don't come in smaller than this, I don't think, for like buying. But if you wanted to build your own circuit with and have something that performed the function of adding two 4-bit numbers together, then they're $15 on Amazon. Okay, we're gonna do, so to finish, or for the last part of class, what we're gonna do is do some word problems together and build a circuit from some description. So I've got one prepared here. I've got 2 prepared here, but we'll do just one of these right now. Don't want to spoil ourselves. Okay. So I'll give you guys several minutes to attempt this on your own, and then we'll do it together. So what you're going to do is come up with a table of operations for this circuit that they're describing. Wow, that's really bad. So there's 3 inputs. We've got sending a request for a new product, input A, warehouse B having the product, input B, and C having the product. And then there's 2 outputs. Table of operations. Someone from that represent this table of operations. Sorry, excuse me. Come up with a circuit that represents that functioning. So give this a shot on your own, guys, just to see how, just to figure out what maybe you might be having trouble with, but try it on your own, and then we'll do it together. And I'll be right back. So figuring out the input outputs for this problem can be challenging in itself. So try and conceptualize how this is actually working before you put down the inputs and outputs. So how this is functioning is that this distributor is asking for a circuit where if they push a button, a request for product goes out. And then there's these sensors at the warehouses telling the circuit whether the product's there or not. So it defaults to warehouse B. If it's there, then it supplies the product. So A and B are tied to, actually here. Okay. My computer froze for a second there. All right. So inputs A and B are tied to output D, and inputs C and A are tied to output E. So when both are 1, then the output's 1. Actually, sorry, no, the outputs. We'll do D first. So when A and B are 1, then the output's 1. Otherwise, it's 0. So 1, 1, 0, 0, 0, 0, 0, 0. All right. So you have to remember this otherwise functioning. So D is the default. So if they're for this first scenario, E is 0, even though there's a signal to resupply at A, and it's got the supply at C, the output's still 0 because D's the warehouse B is supposed to be the default warehouse where things come from. Okay. So this should be how your input-output table looks. Yes, Reese.
Why wouldn't the third line on E be a 1 instead of the fifth line? Because the fifth line, there's no signal from the warehouse.
Oh, you're right. No, I looked at this backwards. Okay. Yeah, third line is 1. I was looking at B and C when trying to figure out whether that was 1 or 0 on the E output. Okay. So have you guys, how far along are you guys? Have you guys figured out the circuit yet or tried to figure out the circuit? No? Okay. So let's do the next step. So the next step here is figuring out a well-formed formula to match each of the outputs. So our really reliable method for that is using disjunctive normal form. So starting with output D, the disjunctive normal form for that would be, and so here's a tip for doing disjunctive normal form. At least for output D, the inputs don't really matter. I mean, input C doesn't really matter. So the two spots where D is outputting 1, the only inputs that matter are A and B. So you don't have to represent the other inputs. So this simplifies our disjunctive normal form quite a bit. So that's for D. And then for E, all 4 of these make a difference. So we have to represent all 4 in one general conjunct. A and not B, what a terrible conjunction symbol. Whoa, I can't write today. All right. And then the next step is turning those guys into circuits. So this is a matter of translating from connectives to logic gates. So the connective for the logic gate for the conjunction is the AND gate. And that looks like this. And then the NOT gate, I mean, the negation translates to NOT gate, which looks like this. So to build these circuits, for output D, it's simply a matter of connecting inputs A and B to an AND gate that outputs to D. For this other circuit, it's a little more complex. So it doesn't matter what order you put these AND gates in, but the number of AND gates should be the same as the number of conjunctions here. So we've got inputs A, B, and C. B is connected to a NOT gate. The rest are not. Let's put B and C through an AND gate first. And then A is attached to this AND gate. So the idea here is that this circuit will only send a signal to one signal to E if the inputs are 1, 0, 1. So 1 being the operator pressing that button, requesting a resupply, 0 being warehouse B not having it, and then C is warehouse C having this, the product. All right. Any questions about what we just did?
So those can be two separate ones. It doesn't have to be like one big one. Like they don't really go together necessarily.
Yeah, they don't. So you don't have to put them together. In the ones on the PowerPoint slide or the textbook also, they'll string the inputs together. I find it looks nicer when you just make them separate. Yeah. How many of you guys were up last night for the storm that passed through? You were, Maddie? Thomas as well? Yeah, it was really crazy sounding. Never heard anything like it. And apparently a very large tornado was just south of Columbia. Yeah, I don't know if you guys are still in Columbia, but yeah, one passed by pretty close. All right, well, that's pretty exciting. Do any of you guys have, if you guys don't have any questions about circuits and stuff, that's it for today. And make sure to contact me if you guys have any trouble with the homework and stuff. The latest homework, I'm going to put it up today after class, and then I'll have the rest graded tomorrow for you guys. But besides that, I'll see you all on Wednesday.